Hello, my name is Dr. Owen Gall, and I will present today my joint work with Professor Doytsher from the Technion, from the Faculty of Mapping and Geoinformation Engineering at the Technion in Israel. Our work is dealing with the deep reinforcement learning for spatial motion planning in 3D environment. So, what we will have today, and what the motivation for our work. So, we're dealing in 3D environments that currently we're not seeing many works dealing with the spatial analysis in 3D environments. Our research is focused on visibility analysis in this kind of environments. We see today a lot of works related to open terrains, but not many related to urban environment. The problem with urban environments are the fact that they are more relevant to dense, complex, and heterogeneous environments where the visibility problem becomes very crucial one to deal with these complex environments and getting a very fast and accurate solution. This is really an NP-hard computation time problem. We saw a lot of application to these kind of problems, especially in computer graphics, such as fast hidden surface removals, for security applications like the famous and well-known art gallery problems, homeland security problems that we're well known with, and the robotics, which we're more dealing with today, and will present in here, as I will describe, very interesting concept of using deep reinforcement learning solution to the motion planning problem in urban environments, dealing with the visibility problem. So what is the big difference between urban and open environments? So as we can easily understand, the open environments are really large and not complex one, not dense environment, and can be easily modeled with the DTMs that we know, where the urban environment becomes very complicated, as I mentioned before, but we can see that we have a lot of different kind of objects in urban environments, such as building, roads, pedestrians. The environments are being changed very fastly due to infrastructures or any other changes in the environment. We got a lot of uncertainties in the environment, such as moving cars, people, weather, trees, and a lot of changing. And of course, the complex environment, which is a very dense one, bring us to a lot of data in high resolution. It's very problematic to solve the visibility problem fastly in this kind of environment. So many works have been done in open environment. As we can see, we had the DEM models and the sideline computation and surface relationship and openness that have been done by Professor Fischer-Grutzman for urban environment. Also, we're trying to get the feeling of the openness in the space openness index. Other work that have been done for multi-agent visibility, but also deal with only kind of voxel and DEM solution using line of sight, which is offline and not online. We're dealing with online solution in our work. So what we'll show today in our approach is presenting spatial motion planning in 3D environment. We will use the state-of-the-art technology that we well know today in machine learning, which is the deep reinforcement learning algorithms. We tackle this problem, but describing architecture of a network that is combined with the solution of spatial analysis for visibility problem in 3D environment, which is an analytic solution that we got. So you can see today. So our previous work, and I will go briefly by that, is considering a very basic visibility problem in 3D environment, where we take the buildings as 3D boxes and defining some parameterization due to these boxes with specific viewpoint, and we would like the problem. To define it, we would like to, we have the viewpoint and the parameterization of the object. Then we would like to compute the set of visible points from this specific viewpoint, but we would like to do that fast and analytically, and not solving the line of sight problem from each point to each point. So our concept is being able to compute analytically the 3D boxes as 2D continuous curves. We're taking a work that have been done by Elber and just extend it by specific singularities that we got, and solving this problem with the cross product characters, and we're getting a very fast computation and singularity points. We will deal with them in approximation in the corner of the 3D box. This is a previous work that we have done, and you can find it in our journal papers from the past. So we took the 3D object, modeled it in this parameterization, and we can find an analytic solution to what we call visible boundary points, also described as a VBP from now on. So as you can see, for these computations, we took the specific point, we describe the object, the visibility boundaries of these buildings, and you can find the visible areas in no time at all. And we can also we describe and extend it to a visible parameters, which are the visible volumes that can easily really define and found analytically. And as you can see, we can just from the viewpoint find all the visible pyramids for each object, and also getting the overlaps and hidden surfaces in a very complicated areas, even in dense environments. So that's our very fast visible solution to the visibility problem in 3D environments. It may be demonstrated in different kind of environments, with trees, without trees, cars, etc., uncertainties. But today we're going one step ahead, and we take this planner using these visibility boundaries that we can compute on real time, and we just integrated to the visibility planning process called the visibility velocity obstacle method. So we can avoid occlusions and of course obstacles, but mostly occlusions, and being able to plan 3D spatial analysis with dynamic model of the platform that we would like to do that with it, and describing the velocity obstacle problem and defining the attainable velocities that we can choose in the next time step at each time. We're using the tree search and defining a cost function to maximize our visibility. By taking this kind of planner, by integrating it into reinforcement learning network, and deep reinforcement learning network, as we will describe, we get very efficient and fast solutions to visibility planning in real time in this planner. So as we can see, we can on the planner itself, we can put one step, avoiding occlusions and ignoring unsafe states by choosing these kind of maneuvers, but we also can maximize or minimize our cost function in satisfying our dynamic constraint. In this case, our cost function is our capability of choosing the most visible solutions based on our analytic solution for the problem. So we would like to take into account the dynamic model constraint. So we took the Dobbins model, which is a well-known one for UAV in this case, which limits the ability of the platform to being able to speed up or to climb or to change. It's a simple car model, well-known in the literature, but it's not an harmonic one, and it's got a lot of constraint from the dynamic and kinematic capabilities. So, as we mentioned, we compute one step at a time. This is a planner, but this is only the basic stage. since we are integrating that into a deep reinforcement learning that we'll describe later on. So the visibility velocity obstacle is just a transformation from the visibility boundaries space to the velocity space. We take all the visibility boundaries pyramids that we mentioned earlier and just transfer it to the velocity space. And by that, we are able to choose and understand what are the visible parts in the velocity space and which are the invisible parts in the velocity space. So as you can see from this point, we just on the left side, just taking the visibility boundaries and just transfer it into the velocity space. And for each object, we get the visibility velocity obstacle. So what is the planning method? We need to check in the velocity space what will be the velocity that will be inside the VVO. So we are looking for such a velocity that will be outside the VVO, satisfying the UAV dynamic, which is the Dobbins model, being optimizing our cost function on the local search. So for point mass model, the relevant and the applicable velocities that we can choose for the next time step is the just simple integration ahead of time of a point mass model. And we get just a rectangular, as you can see here, a basic one, which is a point mass model. But when we are moving on to the Dobbins model, we're getting this kind of a slice of a cake, integrating the model for the 8 possible nodes that we can choose our slice, and you can see that that in our local search, which is a grid search planning, we are just testing all these 8 applicable velocities, and we are looking for the one that will be outside the velocity obstacle, and we'll get the maximize or minimize cost function that we're choosing. So the red points in here are not applicable for the next stage of the tree search, which is a grid search in this case. So the cost function that we're defining is one that will minimize the invisible parts from the viewpoint. So we take each state and define what will be the most, what will be the sum of the all the invisible parts from each point. We can analytically very, very fastly compute that, and that's the strong ability of our method related to other works that have been done till today. And we can just choose the one that takes the solution that we would like. But this is a local planning search we combine with the analytic solution to the visibility problem that we defined till now. So now we take all that and put that into the reinforcement learning, or more precisely, the deep reinforcement learning networks that we got. So the basic reinforcement learning, as we well known, is taking some state of an agent and trying a different kind of policy, and the policy that will bring us to the most relevant solution that we got will be our rewarded, and the agent and the network, the DNN, just learned over time what will be the most relevant policies according to the states, so we will get the optimal solution. So above that, this is the description, the more mathematical description of what I've described now, based on the Markov decision process. In our case, we take a deep reinforcement learning with a fully connected network. So we started with the state space of with 2 hidden layers. So the outputs of 4 actions that we can choose one of 4 actions in our deep reinforcement learning. We train this network with different kind of solutions, and you can see here the simulation results for different kind of states from the beginning to the endpoints of the car model, which we tested out a lot of cases, but this is just specific scenarios. So the trajectory that we can see in here is the one that with the maximal visibility based on the velocity obstacle and the analytic solution of our visibility problem. We can see here another scenarios. Of course, the safety is and the velocity obstacle integrated into the car model, dynamic and kinematic constraint. You can see the smoothness of this kind of trajectories due to the changing of the velocities and acceleration. So we can conclude that in this paper we presented the spatial motion planning in 3D environment that we based on the deep reinforcement learning algorithm. We took the 3D motion planning problem and learns the agent and environment constraint. This spatial analysis focus on visibility environment, setting an optimal motion planning primitives at each time step. So we can get the exact visibility analysis for motion primitives over the trajectory that we're looking for. And based on the reward function, we also get the obstacle avoidance trajectory. We presented here the formulation learns the value of the function of the planner. In this case, was the maximization of visibility. Which future work can also focus on time optimal fuel consumption aspects for future work in this application. Thank you for your attention. If you got any questions, please write us. Hope you enjoyed.